Hello, mathletes. So, we're back in 4.5 one more time, and we're dealing with the shape of a graph using derivatives. And this time we're talking about derivatives tests to find extrema. So we talked about extrema before. We talked about local or relative extrema, and we kind of figured out how to find those. We know how to look at them graphically, the peaks and the valleys. And then we talked about absolute extrema as well, and we talked about critical points being where the derivative equals zero, the first derivative equals zero, or where we have the derivative is undefined, right? And we did find critical points, we did find extrema, especially in the case of absolute, because we can find the critical points, find the critical points, and then plug those values into the function. And we can find the endpoints and plug those into the function, and then we can see just by comparing which one's the highest, which one's the lowest, right? And we did a little bit of relative or local extrema, but sometimes we either need to find a graphing utility, or we may not know which one. It may be sometimes hard to tell whether it's a max or a min, and so that's what the derivative tests will help us to do. Okay, so if we have a function, then and we have our ups and downs and different types of points here. So this is a good example of some different values here, right? We have a situation where we have a critical point where the derivative is undefined. We have critical points where the derivatives are equal to zero, right? And so if we're trying to find extrema, there's really two ways to evaluate whether we know that extrema potentially happens at critical points, but there's a couple ways where we can determine whether the extrema is a max or a min without having to compare all the values of the points. Okay, so one is the first derivative test, and what you basically do is you just figure out, well, is the first derivative increasing or decreasing on either side of those critical points? So you'd find the critical points first, and then you would determine on the interval leading up to that critical point. So let's say we're using critical point A in this case. So here we see that the derivative is increasing on the left side of the critical point, and it's decreasing on the left side increasing on the left side of the critical point and decreasing on the right side of the critical point. And so if it's increasing on the left, decreasing on the right, that means it has to be a maximum, right? It's going up on the left, coming down on the right. That's going to be a maximum, right? It's going to be up on the right, down on the left, okay? And so that's what a maximum is, where you have increase on the left, decrease on the right. The next critical point, B, we can see that the reverse is true, right? It's decreasing on the left and increasing on the right of that critical point. And so if it's decreasing on the left, increasing on the right, then that means that we have a minimum value going on here. Okay, so that would be a minimum. Okay, and then whereas this other one was a max, right? Okay, and you can see, and we know this, but increasing means the derivative is greater than zero, and decreasing means the derivative is less than zero, right? And so if the derivative is less than zero on the right and greater than zero on the left, it'll be a maximum. If the derivative is less than zero on the left and greater than zero on the right, then it will be a minimum value. Okay. Then you have a situation like a critical point C, where the derivative equals zero, but the function is increasing on the left and increasing on the right of that critical point, right? So if it's increasing and then it's increasing some more, then what we have there is we have neither a max nor a min, right? It's actually a point of inflection. You can see it goes from concave down to concave up, but it's not an extrema. It's not a max or a min. So it's so it'd be neither a max or a min. I'll just put let's see, what should I put there? We'll just put a dash. All right. So then once again, back to here, we see this is a place where the derivative equals zero. So, but like the first one that we evaluated, here we have increasing, the function's increasing on the left of this critical point, decreasing on the right of this critical point. So so when it's increasing on the left, decreasing on the right, that means we're going to have a max. Okay, so similar to the one that we had before, but the difference is this one we have a slope of 0 at that point, a horizontal tangent line. Here we had an undefined value where we had a sharp point, or just a point in general, and so that's where the derivative is undefined, but it still produced a maximum in that case. All right, so those are the that's kind of what we're looking for. So the first derivative test basically tells us if the derivative is positive on the left, this just means left of the critical point, and yeah, so positive on the left and negative on the right. Okay, positive on the left, negative on the right. That means you have a local maximum. If it's negative on the left here and positive on the right, then you have a local minimum. And if it's the same sign on both sides, on the left and the right, this is the left, this is the right, then it's neither a local minimum nor a local maximum. Okay, so that's what the first derivative test tells us, theorem 4.9 in the book. Okay, so just a real quick problem solving strategy. The first thing we want to do is find all the critical points like we've done before. Okay, and then we can divide our the intervals into smaller intervals, right? So like, for example, on this last one, we could say negative infinity to a, right? Since this point a here, then we would go a to b, right? So from a to b, and then we would go from b to c, and then we would go from c to d, and then we would go from d to infinity. Okay, and what we do is we just figure out, is the derivative positive, negative, or 0 in those intervals. And actually, we know they're not going to be 0 because we would have already found all the zeros, or the undefined, the critical points. And so we know that the derivative would have to be positive and negative in these cases, right? And we can see that it was positive here, negative here, positive here, positive here, negative here. Okay, so it's positive, negative, positive, positive, negative. Okay, and then from there we can figure out, okay, plus on one side, negative on the other. This is going to be a max, right? Negative on one side, positive on the other is a min. Positive, positive means it's none of the above, and then positive, negative again is a max. Okay, so that's kind of how we would figure that out. All right, so yeah, so then we'd analyze the sign just like we just talked about a minute ago, and then we determine based on this whether we have a maximum, minimum, or neither at each of the critical points. All right, so that's the first derivative test. So we'll try that out. The first derivative test, the good thing about it is it's a little more comprehensive and foolproof than the second derivative test. The second derivative test is maybe a little less work and a little bit easier. I like the second derivative test. That's kind of my go-to. But there are times when the second derivative test is inconclusive, which we'll talk about. And so the first derivative test is a good fallback in case that doesn't work. Okay, and it's just a matter of kind of plugging in values in each interval and figuring out if the derivative is positive, negative in each interval, and then kind of determining what it is on either side. And then you can know if it's going up and coming down. That's like a peak, right? Up on one side, up on the left, down on the right, or or a maximum. If it's going down on the left, up on the right, then it's a minimum.